Chapter 4 brings us into saturation and condensation. And once we start to talk about condensation, we'll be starting to talk about precipitation and doing forecasting for not only condensation but for precipitation. So in going there, let's start with a folk rhyme that is hundreds of years old and that has some really high quality predictive power to it in the Northern Hemisphere. And over the next few weeks, we're going to understand why this folk rhyme has such great predictive powers. And the folk rhyme is this: when the dew is on the grass, rain will never come to pass. When grass is dry at morning light, look for rain before the night. In looking into chapter 4, we're going to understand more about dew. In looking into circulations of air, we're going to understand more about that morning and afternoon impact here. So I introduced this rhyme to you. It's like many great folk rhymes. It's very valuable. And let's learn more about dew along the way. Dew is very important and it's really critical, and it's so much easier than relative humidity. So let's go first of all with why it is important. What you see up here is a meteogram from Morristown Airport, and these meteograms are much like meteograms in 5,000 other small airports across the country. They look at temperature at the top, and right below temperature, they look at dew point. Dew point is a temperature, and it's a temperature at which condensation, or dew, starts to form on surfaces. It is a measurement, it is a temperature, it is not a calculation like humidity is. So it is much easier to understand. And just to get off track for a second, in case you were wondering about the importance of this meteogram, it is right on your homepage in weather.gov by your zip code. You go right down here, and it's right here, the meteogram that is closest to you. Mine is Morristown, New Jersey. This is what's called a localized aviation MOS, model output statistics. And what that is just the simplest kind of predictive model that looks out about 24 to 36 hours ahead for anywhere for about 5,000 airports around the US. It's a very simple model, and you can find it here if you're looking for it, and you can find some great information on what's going to happen hour by hour over the next 24 hours. To get back to dew point, that is so much easier. Dew point as a temperature, as we said, is where condensation starts. A form of condensation is dew. And what we note here is that we can start at the surface on a hot day, and we can measure the temperature of the dew point, and the dew point would be much lower, 60 degrees Fahrenheit versus 92 for the hot day at the surface. If we go up 3,000 feet on a hike, then you would find that the temperature at 3,000 feet would of course be lower at altitude, but the dew point stayed the same. Dew point's the same temperature. If you go up to 6,000 feet, where you might find a cloud because the temperature of the environment matched the dew point. And when the temperature of the environment matches the temperature where condensation starts, then condensation is going to start, and it will produce a cloud at altitude. Fog is just a cloud at the surface and is a form of condensation. A cloud is condensation at altitude where the environmental temperature matches the dew point temperature. So we're explaining temperatures, but let's really get into what the dew point is. The dew point is a temperature to which the temperature of the environment needs to drop down to in order to condense vapor. So while we were at the surface, the environmental temperature was much higher than the dew point. When we went on our hike, the environmental temperature came closer to the dew point. When we got up to about 6,000 feet, the environmental temperature at the higher altitude reaches the dew point, and you can condense vapor. You can, what we call meeting the dew point and condensation results. Along those lines, you're also saying that when the environmental temperature meets the dew point temperature, the air in the environment gets saturated with vapor. Now, you've heard that before. You've heard the term saturation before. And in fact, we talked about saturation and the saturation vapor pressure line that looks at temperature and matches the saturation vapor pressure to an actual vapor pressure in the environment. So we've looked into this before. But when we look into this with dew point, you recognize that the job one of dew point, the most important part of dew point, is to tell you something about the amount of water vapor in the air. The amount of water vapor in the air. Let's look into that a bit more. I've got 4 columns here. I've got various dew point temperatures that range from low to high. I've got actual vapor pressure right here. So what I have here is I have the temperatures, dew point temperature here, and I have my actual vapor pressure right here. So I'm mimicking my graph. Then I've got a calculation based on this graph of an approximate water vapor concentration, and then some information about where and when these different water vapor concentrations happen. And I've got another column about the impact of these concentrations. So let's look into that a little bit more specifically. Start at the top where we see the dew point temperature of 25 degrees Fahrenheit. If we look at 25 degrees Fahrenheit here, it's right about here. You start at about 25 degrees Fahrenheit, go up to the saturation vapor pressure line, and then you move to the y-axis. And you see that that y-axis point is at about 5 millibars. That's the actual water vapor pressure. That's the actual vapor pressure. So that's why I put that in here. We can extrapolate that to about 0.5% because remember we said that normally the vapor pressure for most of the world on average is between 10 millibars and 40 millibars. And 10 millibars out of 1,000 millibars at sea level is 1%. So if we've got 5 millibars, we've got 0.5%. That's the approximate water vapor content. That's what the dew point is giving us an idea about, the amount of water vapor that is in the air. That low water vapor concentration of 0.5% is the normal for Southeast Arizona and is in effect for most of the year. This graphic is out of Arizona State University. You'll come to learn that I love the meteorology department at Arizona State, and I use a lot of their graphics. So it's designed for them. The impact of that, of course, is going to be the desert in Southeast Arizona. It would be called drought anywhere else. And a fire danger because especially the deciduous plants don't have enough vapor to ward off fire and smoke damage. So let's look into this a little bit more closely when we look at a dew point map. So this is a map of what are called isopleths. We'll study that a bit more, but these lines connect similar dew points. This is the dew point that connects all of the areas across the United States that have a dew point at 20 degrees Fahrenheit. And this is the line that connects all the areas that have a 30 degree Fahrenheit line. So you can see that in Southeast Arizona, right by Arizona State University, they have for January and for much of the year, they have a dew point somewhere between 20 and 30 degrees Fahrenheit. And that says that they have a very low actual vapor pressure at 5 millibars and a low water vapor content to their atmosphere. That is job number one of dew point. to tell you about the water vapor content of the atmosphere. Job number 2 of Dew Point is to give you a real feel for the air. And we do this by doing a very quick subtraction of the surface temperature minus the dew point temperature. And that is why on the meteogram from Morristown, you saw temperature at number 1, the first thing you see, and right below it you see dew point. So pilots can do that very quick subtraction. They subtract dew point temperature from surface temperature, and they know that if there's a big difference between the two, like 30 degrees Fahrenheit between the two, which is the same as 20 degrees Celsius, they know that there is not much vapor in the air. And they know that the air has a dry feel to it. This is critical to pilots because it predicts their lift and it predicts how much power they need on takeoff. So you begin to understand a little bit more about the importance of dew point in being able to understand the vapor in the air and the feel of the air. Let's go into another pilot issue which is important to you on flights. Now you will hear all about taking emergency before you get on your flight because it will prevent sickness. And that is just marketing, okay? Here's the science. The way to prevent sickness on long flights is to drink a lot of water. And the reason why you want to drink a lot of water is because of the dew point inside the jet. So what is happening is this: your jet is flying at about 30,000 feet on a long haul, and at that altitude you've got a very low density for the air. Now that you understand this, and when you have very low density for the air, you've got very little water vapor up there, much less than the 1%. So what you have is this jet is taking in air from 30,000 feet and pressurizing it. Just because it gives pressure to the air, that doesn't mean it gives water vapor to the air. And so what you are finding is that the temperature inside the jet is a nice warm 68 degrees Fahrenheit, but the dew point of the air is 5 degrees Fahrenheit or even less at 30,000 feet. And you've got a 63-degree difference, a huge difference between your environmental temperature and your dew point temperature. The result of that is very, very dry air. It means chapped lips and itchy skin and dry mucosal membranes, which is why you get sick on the flight, because your mucosal membranes can't keep the bacteria and viruses out. So all you have to do is drink a lot of water on your long haul flights. You don't have to spend money on emergency. Let's talk a little bit more about what is common around this area. In many areas of the U.S. during the summer, you will note a dew point temperature between 65 and 75 degrees Fahrenheit. If you look at that on your chart at about 65 to 75 degrees Fahrenheit, you're right around here. And you go up from your temperature degrees Fahrenheit up to the saturation vapor pressure line. And then you look to the y-axis and you come in right at 25 millibars for your actual vapor pressure. So I have in here 25 millibars for an actual vapor pressure from this column. That equilibrates to a water vapor concentration of about 2.5%. And that is very common in the normal growing season for much of the country. Just to let you know that, here's what I'm looking at. I'm looking at this area for a dew point between 60 degrees Fahrenheit and 70 degrees Fahrenheit, right in the breadbasket of the country. And oh, by the way, you do feel that is humid because it's less of a difference in the surface temperature minus the dew point temperature. So that means that there is less of a temperature drop needed to saturate the air, meaning you have more vapor in the air, which, oh, by the way, comes up from the Gulf of Mexico through this area. And as a result, it's a clammy feel to the air. The humidity is up. I'll talk to you more about this on the next video. Before I go, the reason why this dew point map is different from the last one, this dew point map is for July in the United States. So there it is. Talk to you later.